Okay, so we've been talking about linear elastic finite element analysis in the context of 3D elements, although last time we did an example of 1D, and we arrived finally at the ability to assemble the global system of equations that we're trying to solve. So from the previous lecture on that assembly of global equations, we have what you're seeing here. So recall, we have a three-member truss, and on this bottom left corner, it is pinned in both the x and the y directions. On this bottom right corner, it's pinned in the y direction and it's pulled on in the x direction with the force P. And then in the upper right corner here, it's pinned in the x direction and allowed to freely move in the y direction, right? So what we want to talk about in this lecture is how do we go about, now that we have the system of equations, which I'm showing you here, so if you don't remember how we got to this point, go back to the previous lecture and review it. But this was the global set of matrix equations that we arrived at by developing the element solutions for each element 1, 2, and 3, where element 1 connects node 1 to node 2. Element 2 connects node 1 to node 3, and element 3 connects node 2 to node 3, okay? So remember, we have 6 degrees of freedom. Each node has a x direction and a y direction degree of freedom. And so that those nodal displacements are contained in this displacement vector. And then there are the forces and the reaction forces that are in this force vector, okay? So the question that we want to ask is how do we apply the boundary conditions? And first, let's just write down what the boundary conditions are. Okay, so what are we trying to apply first? So what are the boundary conditions? Okay, so what are the boundary conditions? Well, let's see. And this, for node 1, so that's in the U1 and the V1 directions, it's pinned. So we know that those are 0. So let's go ahead and write the displacement boundary conditions first. Okay, that the displacement boundary conditions are going to be that U1 and V1. What else? Let's see. Let's go up to node 2. It's free to move in the y, but it is constrained in the x. So U2 will be the same, will be 0. And then finally in node 3, I can freely move in the x, but not the y. So V3 is going to be constrained to be 0. And they're all going to be 0 in this case. Okay? And then how about the force boundary conditions? Okay? Well, what do we know about, let's go up to node 2, right? So there aren't any force boundary conditions at this corner because we've applied displacements. Up here, where we don't have a displacement boundary condition in the y, so we must have a force boundary condition. But there is no applied force, so we only have a net force. And we know that there's no acceleration term, so that net force must be 0, right? So this is equivalent of a free surface in a 3D element. So our first force boundary condition is going to be that F at node 2 in the y direction is going to be equal to 0, right? And the only other force boundary condition we have is in the x direction on node 3, and that's where it's going to equal P, right? So we have F of 3 in the x direction is going to equal P. Okay, so those are the boundary conditions that we want to figure out how to apply here. Okay? So I'll just remind you of something that I hopefully you learned in your intro class. But every single node is either under a displacement boundary condition or a force boundary condition. Maybe boundary condition is the wrong word. For any given node, if there's no constrained displacement and there's no applied force, then the sum of the forces at that node must equal 0, right? So any sort of a free surface is going to give you a 0 force constraint. And otherwise, it's going to equal whatever the load you're applying at that node is, okay? So I'll give you that, remind you of that at the very end as well, but I just wanted to point that out here as we're going through the developing the boundary conditions, okay? Okay, so here's the upshot, is that this is really typical. So it's just typically, right? Typically we have displacement boundary conditions and force boundary conditions. Maybe boundary conditions is the wrong word, but we have we have knowns and unknowns in both the displacement vector and the force vector. And so we can't just invert this stiffness matrix and solve it, okay? So typically, we have knowns and unknowns in both the displacement vector u and the force vector f. Okay? And the implication there is that we just can't simply invert and multiply. And what I mean is that it's tempting to say, well, I can just solve for u as k inverse times f. Right? Well, the problem is that you don't know all of u, and you don't know all of f, so this doesn't work in this way. Okay? So how do we go about applying those boundary conditions? I'm going to give you method 1, which is the method that you probably learned in your intro class, just because it's really simple. Okay? So let's talk about each method, and then we'll use the second method, but I want to refresh your memory with the first. Okay? So here's method 1. Method 1 is to modify the equation directly to directly write the displacement boundary conditions. Okay? So what do I mean by that? That means that I'm going to write directly that u1 equals 0, that v1 equals 0, that u2 equals 0, and that v3 equals 0, right? So what that means is that in this first term here, this first set of equations, I'm going to rewrite that set as u1 equals 0. I'm going to rewrite this set as v1 equals 0. I'm going to write this the third set as u2 equals 0. And I'm going to take this final equation and write it as v3 equals 0. So how do I go about doing that? Let me show you. Okay? So all I did was change those rows to write these equations, right? So this row here says u1 equals 0. What did I do? I just put a 1 in the diagonal where u1 is, right? And this is the v1 equals 0 equation, the u2 equals 0 equation, and the v3 equals 0 equation. Okay? So now it's in a position where I've sort of created all of my unknowns in the displacement vector. So in this case, we have to solve for these. And I've made all my knowns in the reaction vector. Right? Now, one thing I haven't done is I can't go back and ask the question, well, what force what force was induced by setting u1 equal to 0, which is an important question that I want to be able to answer. So this just is one way to let me solve for my u vector, okay? So the way this would work is we would now go ahead and solve this modified matrix equation. Okay, so we would go ahead and solve the modified equation, right? That looks like u is going to be equal to k, and I'm going to put mod because this is the modified k, inverse times f mod, right? Because that's modified as well, right? This no longer looks like the force vector. And I also just say this was just direct, these two, were direct substitutions of the forces, right? We said that those forces were given by 0 and p, okay? So if I go in, I can go ahead and solve for u. Once I have u, then I can go back to the original equation to solve for the f, right? Then you have to go back to the original k to solve for f. So what that means is that we would say that f is going to be equal to k, the original k now, times the u that we just computed here. Okay? All right. So there's some issues with using this on a large scale, even though it's very simple to implement. Okay? So let's talk about these issues. Okay? Number 1, it destroys the symmetry of the stiffness matrix. Okay, why is that important? Because if we have a symmetric stiffness matrix, we'd only need to store half of it, which obviously in a problem that's only 6 by 6, who cares? But if you have, let's say you have 1,000,000 elements. That's not an uncommon number. You have 1,000,000 elements in a 3D model. And let's just, for the sake of argument, say that that corresponds to 1,000,000 nodes as well. Remember, each node has 3 degrees of freedom in a 3D model, so that's now 3,000,000 degrees of freedom. Now you have a matrix that is 3,000,000 by 3,000,000, right? So that's 3 times 10 to the 6th. So you have 9 times 10 to the 12 components that you're trying to store. That becomes very large. So we like to have symmetric stiffness matrices to reduce the amount of storage that's required. So in this case, we increase the storage space required. Number 2, in addition to not having a symmetric stiffness matrix, so we have to store the entire thing, we also, as you can see, when we modified K, we destroyed the original stiffness matrix, right? So we actually have to store the modified and the original stiffness matrix, right? Because we needed to store K so we could get the reaction forces, that force vector, after we solve for the displacements. Okay, the other thing that's of issue that's not obvious just from how we've written it here because we chose convenient numbers, but oftentimes this is going to result in an ill-conditioned matrix for inversion, right? So something like a 1 on the diagonal might be many orders of magnitude different than the other non-zero terms in the matrix. Okay, theoretically, this doesn't matter, but in practice, computationally, it does, because now you have you're going to end up with round-off error that starts to be significant or more significant than the actual components that you might have in your matrix. So this is going to cause you problems in the long run, so it's not an ideal solution to take. Okay, so then the question is, what's another method that we might use? So let's think about that. So let's call this method 2. We'll call this rearranging equations. Okay, and it's going to be based on the following. We have a set of equations in this case that looks like K times U equals R, or F rather. Okay, KU equals F. And rearranging equations is going to break the matrix and the displacement and force vectors into submatrices and subvectors. Okay, so we're going to break it into the following. We'll call this K11. I'm going to put superscripts to indicate that this is a submatrix. K12, K21, and K22. And I'm going to put a dashed line to indicate that it's a submatrix, not just values. Okay. Times, we're going to break the U up as well. We'll have U, let's see, this first one will be UC, and this is going to be part of the submatrix, or subvector rather, and then we'll have UX, and I'll define these for you in just a minute. And then over here we'll have FX and FC. Okay? So let me define, these will come out, you'll see, I don't have to define those specifically, they'll be dependent on the nature of the boundary conditions, but in particular, UC is going to be our known or prescribed displacements. Okay, UX is going to be our unknown displacements. Okay, FC is going to be our known or prescribed forces. And F, as you might expect now, X is going to be our unknown forces. So what do these represent? Let me multiply these out for you. So this matrix equation represents, okay, the following. It represents, the first equation would be K11, right? That matrix, it's a submatrix rather, times the subvector UC, right, plus the submatrix K1, 2 times the subvector U sub x is going to be equal to the subvector F sub x. And the second equation is going to be K21 times U sub C plus K22 times U sub x is going to be equal to F sub C. Okay, so let's go ahead, call this first one equation 1, call this second one equation 2. And now what we want to do is we'll solve this second equation for U sub x. That's the unknown displacement, right? Okay, so we'll say solve equation 2 for U sub x. Okay, and when we do that, we end up with the following. U sub x is going to be equal to, let's see, we'll have the quantity Fc. Remember, that's a known force, so there's nothing to compute there, minus K21, that's just a known submatrix, times UC, the known displacements, that quantity times the inverse of K22. Okay? We'll call that equation 3. Okay, so we're going to go ahead and solve for our unknown displacements using equation 3, and then when we want our unknown forces, we just use equation 1. So after solving equation 3, just substitute into equation 1 and solve for f of x. Okay? So it's just by direct substitution. So let's, if you're like me, the other method seemed very easy even if it wasn't convenient. This method, while I agree seems more convenient, doesn't seem very easy to implement. So I'm going to actually try to walk us through doing this on our example problem. Okay? So let me pop that original equation up for us real quick. Okay, so here is the equation, the original equation that we had, right? So let's think about what we want to do with it. Okay, so we want first we want the grouping to be as follows. We want all of the known displacements to be in the upper part of this vector, all the unknown forces to be in the upper part. Okay, so how are we going to go about doing this? Well, we know that our force terms, we want the known forces to be in the lower part and the unknown forces to be in the upper part. So if you recall, we didn't know F1x, we didn't know F1y because we did know U1 and V1. We also didn't know F2x but we did know U2, right? So these three columns these three rows rather should remain unchanged, right? But I want my unknown forces to be at the top half of this vector, right? So what do? This is the only other unknown force I have, so I want to move it up, right? So I want to take this row and I want to move it right to there, okay? So I want to move the last row and make it the fourth row, okay? So I'm going to make that the fourth row. I'm going to shift the others down. That's all I'm going to do. Okay, so let me show you how we do that. Okay, so what have we done here? So all we've done in this case is we took row, our original here, row 6, right? And we made it our row 4. So that's what this is right here, right? That's all valid. Then we moved row 4 to row 5 and row 5 to row 6. And what that did was it made our force vector such that the top 4 are our unknown forces, F sub x, and the bottom 2 are our known forces, F sub c. So what's needed now is we need this displacement vector in a form that where we have our known vectors up top. So we know U1, V1, U2, but somehow we need to get V3 here and then shift these down, right? So how do we do that? Well, we see that this is multiplied by a matrix, so we can switch the order here by switching the order of the columns here, right? So what we really want is we want this 6th component to move to the 4th component. So what we really need to do is to take this row and move it right here and then shift these others back, right? So move the last, column, I mean. We want to move the last column and make it the 4th. Okay? So let's do that. Okay, so here we are now. So there's what we had to start with. Here's my dashed line. And now I can make a dashed line here, right? So these represent f of x, f sub x rather. And these represent f sub c. Okay? These bottom two quantities, they represent u sub x. And these top 4 quantities rather, that is u sub c, right? So now, and the other thing I'll point out is that when we've done this, we've actually got back to a symmetric stiffness matrix, so we can still only have to store half the matrix, right? So what we end up with is we have our submatrices that look as follows. All right, so we break our submatrices down like this, and then similarly like this. Okay, so this 4x4 matrix, that's the K11. This 4x2 matrix, that is K12. This 2x4 matrix is K21, and this 2x2 matrix is K22. Okay? So the only thing now we have left to do is, since we know these values, we can directly substitute them in. And when we do that, our equation looks something like this, where we've substituted the zeros in for our displacement. We've left these displacements as our unknowns. We've left our unknown forces as unknowns, and then we've substituted in 0 and p for our known forces, okay? So whatever p happens to be, I didn't give you a value, I guess we would have to go in and solve that. But that really is the manner in which it's solved. So you're gonna first solve for the unknown displacements u sub x. You're gonna plug that back into the equation for the unknown forces, and you should be good to go. Okay, so that's the method of modifying equations. This is the method I'd like you to code up and use in your finite element code that you'll be writing for this class. Okay, so again, I just want to remind you that there is no such thing as a node degree of freedom that doesn't either have a displacement that you should write down or a force that you should write down, right? The internal nodes must sum to 0, right? Those forces must go to 0. And free surfaces must have 0 forces on them, right? So that certainly populates a lot of your force vector in a large 3D model, okay? So hopefully that's clear. Hopefully you can kind of go back through, maybe rewatch the video, work through how to do this in sort of an automated fashion in your code. And then the next step after this, now that we've talked about how to actually go about applying these boundary conditions, and this also gives us our solution. Now, once we have our solutions for displacements and forces, the next step is how do we go in and extract other quantities, something like stress and strain that we might care about. So we're going to talk about that in the next lecture.